Today we're going to talk about the difference of squares. So the objective, after we're finished with today's lesson, we will be able to factor binomials in the form of ax squared minus c. So just a quick refresher, if you have something like example 1, x minus 7 times x plus 7, when we distribute that, x times x is x squared, x times 7 is positive 7x, negative 7 times x is negative 7x. Negative 7 times 7 is negative 49. Our 7x and our negative 7x cancel out, and we're left with x squared minus 49. So remember, distributing is multiplying. So today what we're going to talk about is the difference of squares. So questions in the previous examples were difference of squares. The difference subtraction of two perfect squares. So if we have a plus b and we multiply that by a minus b, we got a squared minus ab plus ab minus b squared. When we got rid of our two center terms, we were left with a squared minus b squared. So today what we're going to do is we're going to start with that binomial, a squared minus b squared, and we're going to factor that. So we are doing the inverse of distributing, and we're going to factor. So if we have a squared minus b squared, and those are both perfect squares, we will result with one of our factors being a plus b, and our other factor will be a minus b. So let's take a look at example 5. If we have x squared minus 25, is it possible to factor this? So the first thing that you want to ask yourself, is x squared a perfect square? Well, yes. X times x, two of the same thing, multiply together to get us x squared. Is 25 a perfect square? And we say, well, of course, 5 times 5 get us 25. So when we factor the difference of two perfect squares, our a, or our first term in our parenthesis, is going to be our x. Our b, so if I rewrote 25 as 5 to the second power, would be 5. And the signs in both of our parentheses, one needs to be plus, one needs to be minus. If you distribute this back out, you can see that x times x is x squared, x times negative 5 is negative 5x, 5 times x is positive 5x, and 5 times negative 5 is negative 25. Our center terms cancel out, and we're left with x squared minus 25. So we did, in fact, factor that correctly. When we look at example 6, we have 4a squared. So I'm going to ask myself, is 4 a perfect square? Well, yeah, 2 times 2 is 4. So I can actually rewrite this as 2a to the second power, if I'd like. Is 49 a perfect square? Well, yeah, 7 times 7 is 49, so I can rewrite that as 7 squared. So when I put it into my factors, my a is going to go in the beginning of my parentheses, so I will have 2a and 2a. My b, or in this case my 7, is going to go in the end of my two new factors, and I know that my signs have to be a positive and a negative for that center term to cancel out. So when you check this, 2a times 2a is 4a squared, 2a times 7 is negative 14a plus 14a minus 49, and in fact our center terms did cancel out, and we result with the original binomial that we started with. So the factors of 4a squared minus 49 are 2a plus 7 and 2a minus 7. Looking at example 7, I want to ask myself, is there something that multiplies by itself to get to 3? No, 3 is not a perfect square. Okay, well, what am I supposed to look for first when I factor? Oh yeah, I'm supposed to always look for a GCF first. Well, let's see. 3 and 27, they are both divisible by 3. So if I factor out a 3 first, 3x squared divided by 3 is x squared. 27 divided by 3 is negative 9. Oh, well now I recognize that 9 is a perfect square. 3 times 3 is 9. X squared is a perfect square. X times x is x squared. So my 3 that I factored out needs to remain on the outside because when I distribute everything back, I have to get my original binomial 3x squared minus 27. But then essentially I'm going to ignore my coefficients for right now, and I'm just going to look at my x squared minus 9. So I said x times x was x squared. 3 times 3 is 9, and because this is a difference of two perfect squares, I know one has to be plus and one has to be negative. So now I want to re-look at my problem and make sure it distributes back nicely. So x times x is x squared minus 3x plus 3x minus 9 combines to x squared minus 9. But then don't forget, I have to also distribute my 3 back to these. So I get 3x squared minus 27, which looks like my original answer. Makes me happy. So I know that the factored form of 3x squared minus 27 is 3 times the quantity of x plus 3 and x minus 3. So always, always, always look for a GCF on anything you are factoring first. So when I look at example 8, n squared, oh, that's a perfect square. 100, oh, I know that's 10 times 10. And my middle term eliminates, so I know my signs have to be a plus and a minus. Well, when I distribute n plus 10 and minus 10 and check my answer, n squared minus 10n plus 10n minus 100, my center terms cancel, which is great, but I'm left with a negative 100, and these do not match. So n plus 10 times n minus 10 is not the factors of n squared plus 100. So there is no combination that I can multiply together. If I multiply n plus 10 times n plus 10, that would get me a positive last number, but that would leave me with n squared plus 20n plus 100, so that one doesn't work. If I do n minus 10 and minus 10, that would also get me a positive 100, but that's going to leave me with a negative 20n in the center, so that doesn't work. So if there are no combinations that you can multiply together, or more specifically, if you have the sum of two perfect squares, meaning there is a plus sign in between them, your binomial is prime and you cannot factor it. There is nothing that multiplies together to get n squared plus 100. The last two examples we want to take a look at is example 9. And example 9 says, what is the product of 47 and 53? Use the difference of squares to calculate this. Well, what is a number that is almost the same distance away from 47 and 53? Well, 47 is 50 minus 3, and 53 is 50 plus 3. Oh, beautiful. So, you notice your first two terms in your parentheses are the same. Your last two terms are also the same, and your signs are opposite. So when you distribute this out, 50 times 50 is 2,500. 50 times 3 is positive 150. 50 times negative 3 is negative 150. And negative 3 times 3 is negative 9. So 2,500 minus 9 is equal to 2,491. So if you have two numbers that are an equal distance apart, you can use the difference of two perfect squares to calculate the product or the multiplication of those two numbers. So if we have, or they ask us, what is the product of 98 and 102? Well, in my head, it's very difficult to multiply 98 times 102. But if I rewrite 98 as 100 minus 2, and I think of 102 as 100 plus 2, 100 times 100, do I know what 100 times 100 is? Oh yeah, it's 10,000. Do I know what negative 2 times 2 is? Oh, that's 4. And when I subtract 4 from 10,000, I know I get 9,996. So the product of 98 and 102 is 9,996. You can now finish your worksheet for day 12.